Good morning. Good morning. I'm glad that there are some people managed to get here after yesterday's banquet. But my name is Yuri Pout, and I will be chairing the morning session. And the first speaker is Alessandro Patruno, who will tell us about accreting millisecond pulsars.
Thank you. Can you hear me? Yeah. Okay, so I will talk about accreting millisecond pulsars, and there are 19 systems known, and despite their small number, these objects are quite extreme and can be used for a number of stellar astrophysics, binary evolution, plasma physics, and even fundamental physics tests. So the topic is very broad, and I've selected, of course, some of the highlights of the last few years. They are also important because they are related evolutionary to the radio millisecond pulsars. So these objects that were predicted to exist in '82 by Ali and by the Indian group are basically objects that are created in binaries when a high mass star explodes and leaves a low, slow spinning neutron star. Then the donor star, the low mass companion star becomes a donor star filling the Roche lobe. And it is in this phase that the accreting millisecond pulsars are created. And then after this phase, the low mass X-ray binary phase, the systems should stop accreting and you should generate binary radio pulsars. And now I will focus on these last two steps, also because recently it has been discovered that this process is not unidirectional in the sense that you can switch back and forth between these two final phases. Let me say something about let's say the physical configuration of the system. You have a low mass star that is transferring mass into the Roche lobe of the neutron star, and this plasma rotates in the accretion disk until it feels the magnetic pressure of the magnetosphere of the neutron star, and the gas is channeled towards the neutron star poles. And this radius here is the so-called magnetospheric radius when this happens. Now this is a zoom in of the innermost regions. This radius, the magnetospheric radius, sets the scale of the problem, because when the gas reaches this point, it also transfers its specific angular momentum to the neutron star and spins it up. If the rotation, the angular velocity of the gas here is higher than the angular velocity of the neutron star. If instead this magnetospheric radius is found outside the co-rotation radius, which is the point where the plasma in the disk is rotating slower than the neutron star, then you have the so-called propeller, and you spin down the neutron star. And this magnetospheric radius, of course, depends on the magnetic moment of the neutron star, and that gives you the magnetic pressure, basically, and on the mass accretion rate, which gives you basically the ram pressure of the gas. Now, I was saying there are 19 known accreting millisecond pulsars, and there are, broadly speaking, 4 types. Those that have a main sequence companion and have orbital periods, let's say, larger than about 3-4 hours. And then you have the semi-degenerate companion stars, which are accreting that have orbital periods relatively compact. You have the ultra-compact binaries with wide dwarf donors. And then there is the class of the transitional pulsars, which have been discovered recently, and that I will focus on in a few slides. Now, one peculiar feature of these objects is that their spin is very high, but never crosses a certain threshold around 700 Hertz. Here you see the spin distribution of accreting neutron stars, which I've plotted, including also the so-called nuclear-powered pulsars. So you have accreting millisecond pulsars, but you have also nuclear-powered pulsars, where you basically see detect the spin of the neutron star by looking at burst oscillations, which are generated during thermonuclear explosions that occur on the surface of the neutron star. And there is this limit at around 700 Hertz, And it is well known that this limit cannot be due to reaching the breakup frequency of the neutron star, because any equation of state basically would allow you to generate objects much faster than 700 Hz. They can go up to at least 1,000 for the hardest equation of state. And this distribution is also not really a normal or uniform distribution as it was thought in the beginning. There is this peak here, which is quite significant. And you can basically, I performed some statistical tests in collaboration with Neil Sanderson and Bryn Haskell this year. And basically, you can describe this distribution in this way. So this is the same plot. I've just changed the binning just for display purposes. So you can describe this distribution as made by two Gaussians. Well, this is flat, or if you want. And a narrow Gaussian distribution of very fast systems, very narrow, with a width of only 30 Hertz. And if there's accreting neutron stars are really composed by two subpopulations, then there must be a reason, a mechanism that separates these two populations, why some of them are slower and some of them are faster, and why this distribution is so narrow. And here it's a list of all the objects that the objects that fall into this narrow distribution, and they are basically all very strange systems. These two, pulsar J1023 and 1227, are the transitional pulsars that I will discuss in a moment. Most of these others, the 6 others, are nuclear-powered pulsars, so they've never shown accretion-powered pulsations. This Aquilex one is another very peculiar accreting millisecond pulsar, because it shows pulsations. It has shown pulsations only for about 150 seconds, despite being observed for more than 2 million seconds in total. And this is this is the fastest accreting millisecond pulsar known. Now, let me say something further about these two systems, these two peculiar systems, the transitional pulsars, which are very fast binary pulsars. So these objects, we heard something about them yesterday already from Liliana and Shibanov. And there are 3 or 4, there are 3 secure transitional millisecond pulsars identified so far. And there is a candidate one. And 3 of them never went into a full outburst. So these objects switch between a low mass X-ray binary state and the radio pulsar state. And when they are in the low mass X-ray binary phase, they basically don't go into outbursts. So they shine at very low luminosities of the order of 10 to the 33 ergs per second, which is typical of quiescent low mass X-ray binaries. And when they are radio pulsar, when they switch into the radio pulsar state, they are the so-called, they're identical to the so-called redbacks, which are basically binary radio pulsars with the main sequence companion, which is being irradiated and ablated by presumably by the pulsar wind of the neutron star. And these redbacks also, we heard about them also yesterday. So these redbacks have typical masses of about 0.1, 0.2 solar masses, and they are non-degenerate. And they are very closely related also to the group of black widows, which are also binary radio pulsars, but they have a smaller companion star, and they have a semi-degenerate companion. And these objects are seen in radio, and they are not really filling, the star is not really filling the Roche lobe, but several of these systems are very close to fill the Roche lobe. There was a study from Breton a few years ago where he showed that some of these objects can have filling factors of the Roche lobe close to 1. Now, these objects are important because, all the transitional pulsars are also redbacks. And so if people are looking for transitions in other known redbacks, and these objects are also particularly fast. They're in the high-end tail of the spin frequency of radio pulsars. And recently there was a new radio pulsar discovered with a very fast spin. And these objects basically show also a very steep radio spectrum. So if you want to find new ones, you can look at very low frequencies, and in that sense, LOFR, the radio telescope in the low-frequency radio telescope in the Netherlands, is playing an important role because it can reach very low frequencies and look at the spectrum of these binary radio pulsars. And I want to show you some new object that was discovered by the group of Jason Essels, and there's a paper from Case Bassa on the archive. This is a 707 hertz radio pulsar. This is in a black widow type binary. And this system was discovered thanks to the very steep spectrum, so looking at the very low frequencies. And an important thing to say is that this object, if you look at the location, this is the location in the PP dot diagram. This is a zoom in of the PP dot diagram. There's only an upper limit on the P dot, but this object is in the field, differently from the current record order of 716 hertz that was discovered in 2006 by Jason, that is in a globular cluster. And when you find these objects in globular clusters, you of course have a lot of problems to measure the spin derivatives because you have the gravitational potential well of the globular cluster that contaminates the measurements. This one is in the field, so far there's only an upper limit, but we will probably soon have a measurement and we will know where this object is located. Now, okay, so if these transitional pulsars look like redbacks, people thought also, since black widows are very similar objects, they just have a smaller companion mass, can also black widows show transitions and become accreting objects? So far, none of the black widow pulsars has shown episodes of accretions and transitions. And so if you look, I want to show you something about an accreting millisecond pulsar that has orbital parameters compatible with those of a black widow pulsar. So this is the system SUX-J1808. And the question here is, so this is a 2-hour binary with a 400 hertz spin frequency neutron star. And so the question is, if this system, when the system is not accreting, when it is in quiescent, does it show a radio pulsar? Does the radio pulsar turn on? We don't really know, but we have done 2 tests. The first test that you can do is to look for the radio pulsations. And the radio pulsations, despite some very deep green bank observations that we got a few years ago, shows no radio pulsed emission from this object when it's in quiescence. And this means that the radio pulsar in SUX-J1808, if it exists and it's really pulsating in radio, must be in the bottom 10% dimmest radio pulsars known. So we can exclude that it is in the top 90% bright pulsar population. Also, when you look at the optical data, you see clearly a residual accretion. So you see a residual disk in the system. And in this plot, this is a VLT spectrum taken a few years ago during a quiescent state of SUX-J1808. And you see this double picked the H-alpha line, which is usually the hallmark for the presence of an accretion disk in the system. And this is a residual accretion disk. And these residual accretion disks are not seen in transitional pulsars when they are in quiescence. When they are in quiescence, or let's say when they are in the radio pulsar state, let me be more precise, transitional pulsars show no evidence of accretion or residual accretion whatsoever. So they don't show this type of signature. One can look also at accreting millisecond pulsars in quiescence, which are similar to redbacks, because after all, no black widow, I said, has ever transitioned to the accreting state. So maybe those similar to redbacks would do. And this system, SUX-J1748, is also 440 hertz spin pulsar, accreting millisecond pulsar. And this has a main sequence companion, and it's in an orbit of about 9 hours. So this would be compatible, at least from the orbital elements point of view, to a redback. And in quiescence, again, this looks like a normal quiescent neutron star low mass X-ray binary, and it shows also a residual accretion disk. It shows also H-alpha emission, And in these two plots, you see basically the HST observations that were taken in different epochs. This source is in a global cluster in NGC 6440. So this is the color magnitude diagram of the cluster, and this is the color diagram of the cluster. And this red point is the optical counterpart identified by Cadellano et al. This year. So again, if you take accretive millisecond pulsars, which are compatible at least with orbital elements to redbacks, and you look when they are in quiescence, they still look like normal low-mass X-ray binaries. So what causes these transitions, and what is special about these transitional millisecond pulsars? Now, this is pulsar J1023, which is the first transitional pulsar discovered. This was discovered as a radio pulsar in 2007. And then by looking backward at archival optical and radio optical data, Archibald et al. Found some transition in around 2000. So around 2000, between 2000 and 2002, this object showed a residual accretion disk in optical. And then this system stayed in the radio pulsar state until 2013, when it switched back to a low-mass X-ray binary. And still today, this is still in the same state. However, when I say that this object switched to a low-mass X-ray binary state, this is not really a typical low-mass X-ray binary state. It's very dim. The X-ray luminosity is of the order of 10 to the 33 and shows this flickering between 10 to the 32 ergs per second and some flares that reach up to about 10 to the 34 4 ergs per second. So this luminosity is more compatible with a quiescent low-mass X-ray binary. And these are the three states: the low mode, this bottom one, the high mode at 10 to the 33, and the flare at 10 to the 34. What is special about this light curve is that this is identical also in another transitional millisecond pulsar. Here in the bottom you see the system XSS J12270 when it was in the low mass X-ray binary state. Right now it's in the radio binary state. These two light curves are basically identical. They show exactly the same features, exactly the same behavior. If you look at the spectra, or at both power and energy spectra, and you look at the three different levels, so let me go back, this low, high, and flaring mode, they also are identical. The energy spectrum is in the three different modes, low, high, and flaring modes, are all described by power law. There is a little hint of a black body in the high mode. And also the power spectra are featureless, and they are power laws with a possible break around 1 hertz, 0.11 hertz. And they are identical. There's no difference. This is very different from what you see, for example, in high-mass X-ray binaries, in some high-mass X-ray binaries, like VLX1 that shows switches as well. But in that case, you see a complete change in the X-ray spectral energy in the X-ray spectrum, because there's some material absorbing, and so you could relate these variations to material absorbing in the binary. Here, this is not the case. Also, in this high mode, in this middle luminosity state, the source shows pulsations, which are almost certainly accretion powered, and doesn't show pulsations neither in the flaring mode or in the low modes. This is very peculiar. And now we have been timing this object for several years. And here I'm showing you some new observations as well. So these are basically measurements of the, I see here you don't see it well. This is let's look at this one. This is the spin frequency of the object measured through the years. And this is a baseline of basically a few years since it switched to the low mass X-ray binary state. And the last measurement, these data points have been made with XMM Neutron 2 months ago. And this object shows a spin down, even during the low mass X-ray binary state. And what is peculiar is that the spin down that you see, this new dot during the accretion phase, during the low mass X-ray binary phase, is very close to the spin down that you have in radio. It's 25% faster, actually, so it's spinning down a little bit more. And so far, there is no clear explanation for this. We don't really understand how this works. I mean, there is later a talk from Kyle, so maybe we should see if he has an explanation for this. Another peculiar object is another transitional millisecond pulsar. Actually, the very first one identified as an accretion and a radio millisecond pulsar. This object is also in a globular cluster in M28. And M28 is a very rich, is a globular cluster, very, very rich globular cluster full of millisecond pulsars of all kinds. And this object is a little bit wider, it's an 11-hour. And its peculiarity is that this one, differently from the other transitional pulsars, went into a full outburst. So this, if you look at the X-ray luminosity of this object reached the typical X-ray luminosities of neutron star in low mass X-ray binaries when they go into full outburst. And it showed a typical luminosity outburst that lasted for a few weeks. And the peculiarity is that after the outburst was over, so with these circles you see detections, and these open ones are non-detections in X-rays. And the stars are non-detections in radio, so here it was not a radio pulsar, it was an accreting pulsar. Here it stopped being an accreting pulsar, and after a couple of days it was already on as a radio millisecond pulsar. So the transitions, at least from the low mass X-ray binary to the radio pulsar state, are incredibly fast. And here you see the first detection that was made in Westerbork in May 2nd, 2013. Now, another peculiarity of these transitional pulsars is that they show a very powerful, outflows. Now, here you see this is the famous radio X-ray luminosity diagram for jets that is used in jets. And you see these black dots. These are the black hole measurements, black hole binaries. And it's well known that the X-ray and radio luminosity of black holes correlates very well. And usually this is interpreted as, this radio luminosity as being generated and X-ray luminosity as being generated by a compact jet emitted by the binary. And then you see this big blob of objects which are the accreting neutron stars in low mass X-ray binaries. And what is peculiar is that if you look at these two lines here, these are the predictions that the accreting neutron stars should follow when generating a jet, an outflow. And I want you to focus first on these triangles. These triangles here refer to the transitional pulsars. And these transitional pulsars are very powerful because their radio luminosity is much larger than what was expected to be found based on these extrapolations based on models. Another thing which is interesting are these data points, which are these red stars, which refer to the latest outburst of SAX J1808 observed in 2015. And also this object shows quite strong variability, but also very powerful outflows. And there is this line here that you see, which basically identifies the location where these transitional pulsars were first seen. And now this region is slowly being filled by other objects, other accreting pulsars. So it seems that at low luminosity, at low X-ray luminosities, these objects, these accreting neutron stars with the magnetic field at least, can generate powerful jets. And the reason is still not very well understood. In particular, if you look at one object, this is pulsar J1023, the transitional millisecond pulsar. And this black curve are Chandra data observed last year, that observed the source last year. And overplotted are JVLA radio observations. And if you look at this, you see that there is a very tight anti-correlation between the radio and the X-rays. So when you go into this low mode, there are flares in radio. This is not very strict correlation in the sense that sometimes there are flares in radio which are not seen in X-rays, but when you see a low mode, then the source shows flares. And now you can say, okay, if I take the radio luminosity and the X-ray luminosity here, and I assume that this is generated by an outflow, where would this object fall? And this is the location, this star, where you would put pulsar J1023 when you see this flare. And so it's basically on the same line of black holes. This is the same diagram I was showing before. And this object, of course, opens a number of new questions because, first of all, we don't know how these outflows or jets are generated in accreting neutron stars. There are some vague ideas on what happens in accreting black holes, but accreting neutron stars are still not very well understood. But also it shows that this diagram cannot be necessarily used to identify and distinguish accreting black holes from accreting neutron stars. Some of these objects might even be some sort of transitional millisecond pulsar imposters, if you want. And finally, I want to say a few words on this other object. This is the fourth transitional millisecond pulsar. It's still a candidate. This was discovered in 2015. And again, this is what you see here is the XMM Newton light curve. And you see that, again, this also shows this typical flickering during the accreting state. And again, this now is being used to, let's say, to find new objects. But of course, it's very complicated to observe this flickering if the object is far away. So we actually don't really know whether some accreting millisecond pulsars that we already know would show this flickering at these luminosities because they are pretty far away. These objects are relatively close by. Pulsar J1023 is 1.4 kiloparsecs, whereas most accreting millisecond pulsars are in the galactic center, so are a factor of 5, 6 more in distance. And this object is a candidate because it has no measured spin or orbital, or at least as far as I know, there is no spin measured, so no accretion-powered pulsations. And Slavko Bogdanov also looked at archival data in the past decade and saw no sign of transition. So this object has been in this state for very long. It is also a gamma ray source. It's an unidentified Fermi, well, now identified Fermi gamma ray source. Shows radio emission and has been relatively stable for the past 10 years. Okay. So my conclusions are this. So these objects, these accreting millisecond pulses can be used for a lot of different tests. They show some very peculiar high frequency speed limits in their spin, which is also similar to the speed limit observed so far in radio millisecond pulsars. And the transitional pulsars show a very puzzling new phenomenology from outflows to X-ray light curves to these very strange transitions. There's powerful jets rival in luminosity those seen in black holes. And the quiescent behavior of accreting millisecond pulsar does not really seem to match what we observe in transitional millisecond pulsars. So there must be some missing ingredient that makes this transitional pulsar turn on as radio pulsar and not, and this doesn't happen in several other accreting millisecond pulsars. Thank you.
Questions? Any questions? Sandra.
Very interesting. I have a small comment. Can you come back to the slide with the radio anticorrelated with the X-rays? There sometimes we also see these flares, and the radio is coming afterwards probably, or at least it also has a flare when the X-ray flare is present.
You mean here?
Yeah, it seems that it's
sometimes
not only
it's
anticorrelated.
Sometimes it's not correlated. But what is important is that when you have these low modes, you always have a flare. But then sometimes you see that you see here, you see all this bunch of flares in radio, and they are not related to the X-rays, yes.
But there are also sometimes the radio flares are coming like at the same time or a little bit after the X-ray flare, so it might be interesting to...
Yeah, absolutely, like here, yes.
More questions? Anybody else? Kyle. Yeah.
Just from looking at the light curves, it seems like these things spend most of their time in the high mode and then drop occasionally to the low mode. Do you know roughly what fraction of the time it spends in each state?
Oh, the exact number, no, I don't know, but yeah, you can see it from here. It's like probably 20% of the time is in the low mode, and most of the time is in the high mode, yeah. And these flares, the flares that you see, which maybe are more obvious in the other plots, they occur sometimes in bunches, and sometimes they last for a long time, several hours together. So you see a lot of flares. Sometimes the observations instead are relatively clean. Instead, this low mode and high mode alternate pretty regularly. It's the flaring the flaring activity which is a little bit more erratic and variable. Yeah.
Can I ask about this object? When you say accretion-powered quiescent, do you know the spectrum of this emission? Is it like thermal or non-thermal?
The spectrum is this one. Is basically non-thermal. I mean, it's a power law with an index of 1.7. Okay. In the high mode, you have a hint of a black body, which I think is just because of the pulsations.
It doesn't look like thermal emission from the surface. Just some shock. Anyway.
Yeah.
Yes, question.
Alessandro, could this 700 hertz to be due to R mode instability? Did you check this?
Yes and no. I mean, not me personally, but people have looked into this. It's the usual problems. I mean, you can, if you have R modes, of course, the R modes can put a limit, but there are some systems where this is not observed because the R mode should spin down. I mean, lasts for a certain amount of time. And so when this R mode is active, you should see the star spinning down. And we don't see that. Also, they should make the stars hotter because of this dissipation of energy. And there is not really a clear evidence for this, let's say. I mean, I don't know the details of how the models and how, which one is more realistic than others, but observationally, there is not a strong evidence besides this limit. But there are many other ways of justifying the 700 Hertz. That's the problem.
I have a question about SAX-1808. I remember, I think it was a paper by Borderi a long time ago when they claimed that you see radio emission in the quiescent state of this object. Is it still,
no,
do people believe that?
No, I think what you are referring to is the fact that a radio pulsar was invoked, let's say, in quiescence because you have an overluminous optical companion. And so this must be irradiated by something. And if you look at the X-ray luminosity in quiescence, that's not sufficient to irradiate the donor. And I agree with that. But the problem is that maybe you have a pulsar wind but no coherent radio emission. Seems strange. What is strange is also that other systems, because SAX-1808 is not the only one, there are several others that show an overluminous donor star in quiescence. So if they all turn on as radio pulsar, well, let's say if they all have a pulsar wind in quiescence that is irradiating the donor, why nothing happens to this residual disk? That's really puzzling, and I don't think there's an explanation for that.
Any more questions? Okay, let's thank Alessandro again.
Thank you.
Сейчас включим, будет слышно. Okay, the next talk is by Valery Suleimanov, who will repeat okay, and who will talk about accretion-heated atmospheres of X-ray bursts in neutron stars.
So, good morning, everyone. It seems that X-ray bursting neutron stars is well-known objects, and it's not possible to say something new about them, but I will try. Why it's important? Because its X-ray bursting neutron stars give us a good possibility to measure neutron star radii. It's important for establish equation of state of neutron star matter in the cores. And most of the facts is here. You can see duration of the burst about between 10 and 1,000 seconds for typical one. And here it's light curve of typical X-ray burst with photospheric radius expansion. Here its burst is not stopping, but emission is go to ultraviolet region out of the observed band in X-rays due to strong expansion of the photosphere and temperature decreasing. This is typical phases of X-ray burst. Initial phase when burst start, and then expansion bands phase for photospheric radius expansion bursts, and then cooling phase. So, and here in the light curve, temperature changing and normalization changing using blackbody approximation of the spectra are shown here. And all three phases are shown also here on these curves. And most important point for us is touchdown point, so-called touchdown point, where temperature has maximum value and normalization is the smallest value. It's clear from the common sense that in this cooling phase, the physical radius of the neutron stars cannot change. But what we see here, we see that normalization or blackbody radius of the neutron star change during this phase. Why? It's not observed for all X-ray bursts, but only for the part of them. But it's important to find neutron star radii using this fact. It's arise due to some features of the observed spectra and theoretical spectra of hot neutron stars. You see here that model spectrum of the hot neutron star atmospheres is very close to diluted blackbody due to strong interaction between electrons and photons due to strong Compton effect. But its shape, it's very good blackbody, but shifted corresponding to blackbody with effective temperature to higher energies. And if we feed this spectrum with blackbody, we will see that it's diluted. It's formula for this approximation of the theoretical spectra, and we see that this blackbody with temperature higher than effective temperature. I would like to remember that effective temperature means that this bolometric luminosity is the same for this theoretical spectrum and this blackbody spectrum. Okay, and we see that there are two parameters for this fitting: color correction, which shift the maximum of the spectrum to the highest energies, and dilution factor, which depress this blackbody up to model spectrum. And if we will see how we approximate the observed spectrum with blackbody, we see that this blackbody connected with effective temperature through color correction and through gravitational redshift. And it's clear that this normalization could change only due to this dilution factor. You see this normalization change during this third phase when we believe that physical neutron star radius is not changed. And here in normalization you see that gravitational redshift cannot change, physical radius of the neutron star cannot change, distance cannot change. Therefore, any changing of this normalization arises due to this dilution factor. And it's possible to compute how this dilution factor and color correction factor depends on the relative luminosity, relative to Eddington luminosity. I mean, its color correction factor has maximum at largest luminosities and then decrease with luminosity. And dilution factor has minimum at high luminosities and increase with luminosity decreasing. What we can observe in comparison with these theoretical curves, it's possible, in fact, to fit the observed curves. Here is bolometric flux and here is normalization. It's possible to fit by theoretical curves. But this fitting is possible only for system when X-ray bursts happen in hard quiescent spectral state. You see here for this ultracompact system, two spectral states in quiescence. It's soft and spectral states, persistent emission, and this hard persistent spectrum. And we believe these two cases corresponds to different physical pictures. Optically thick boundary layer for the soft state and some rarefied high temperature accretion flow for the hard persistent state. And we know that observed curves corresponds to theoretical curves only only for burst, which happens in hard persistent state. Here you see two examples for two different sources, and you see that if persistent flux is much more smaller than Eddington flux, so 2%, the deviation is not so high between theoretical and model curves. But if we see in another system, it's very famous ultra-compact system with period close to 12 minutes. We see that deviation starts much earlier than here, and it's much larger in amplitude. Persistent flux here is about 7% of Eddington flux. Therefore, we see that there is some correlation between deviation of model curve from observations on persistent flux. And we try to explain it using this picture. Here we see that some accretion can continue during the burst, and this hot accretion flux can continue to accrete for neutron stars during the burst too. And I believe that we see this deviation due to this additional heating of neutron star atmospheres due to fast particles which accrete on the neutron star atmosphere. The qualitative picture is here. So plane parallel atmosphere is heated by flux of fast particles. It's not hydrodynamical picture, but we have to consider every particle as separate particle which penetrate to atmosphere and lost his energy, release energy. And there are some additional parameters to describe this task. Velocity of accretions, accreted particles, angle of this direction of this velocity, and then we have to know that protons and ions in this hot accretion flow could have temperature close to virial temperature. It's very high temperature, up to 10 to 12 Kelvin, and we have to take into account this some distribution of the particles in the space and in the velocity space. Particles penetrate up to few Thomson optical depths and column density of between 10 and 1 grams per square centimeters. And additional parameter is this accretion luminosity, which arises in this relatively thin skin of the above the atmosphere. And local mass accretion rate could be found from this using these parameters. Short history. This picture was considered many times. The first by Zeldovich and Shakura in 1979, and they shown that energy release will be in the optical depths parts of the atmosphere. And Larkin gave us the correct physical picture how fast particle lost his energy in the plasma due to Coulomb interactions. And this work was the first correct computation of this accretion heated neutron star atmospheres. And here our Italian colleagues gave good contribution in the problem, and postgraduate students of Henrik Spruit gave us some application to try to explain hard persistent spectra of low mass X-ray binary using this physical picture. And we developed our own code, which based on the same code which we compute non-disturbed neutron star atmospheres, and we add some additional energy release in the upper layers, additional force, ramp pressure force in the atmosphere, and take into account electron thermal conductivity. In this formula from Larkin, it's some only main terms, and some results which we obtained using this approach. Of course, there are a lot of parameters. Unfortunately, first of all, it's input. All computations were performed for these parameters of neutron stars, and it's internal some burst luminosity and free fall velocity here, virial temperatures here, and some parameters for accretion flow. Accretion luminosity, it's relative to Eddington. Some parameters which characterized velocity of particles in comparison with free fall velocity, sorry. And here is some parameter which correspond to temperature to virial temperature and angle of the penetrating. And of course, we consider different chemical composition of the accreting matter and atmospheres. That's some example of the computations. You see here it's a spectrum, and it's not flux, but energetic flux. Energy of photons multiplied to flux, nu if nu, so-called. And you see that it's possible to obtain very flat spectra with typical depressions here. It's exponential cutoff. I mean, and you see here's temperature structure of the model atmospheres. And I would like to say with some honesty that our code could give good results and allow to solve radiation transfer where temperature change in 2 orders of the value of the magnitude in very narrow region. And some other interesting things that angular distribution of the emergent radiation, it's a little bit strange, but it's expected that it could be like this. We can see lamp darkening in these relatively low energies, and limb brightening in these relatively high energies. How to expect? Because in this hard radiation arises in this optically some hot upper limb layers, and of course when we see in some larger angle we see more and more energy which comes. It's optical depth of the layers becomes larger, and we see larger intensity here. Of course, if relative accretion luminosity becomes smaller in comparison with internal luminosity of the atmosphere, deviation of the spectra becomes smaller and smaller. And here you see that for models close to Eddington limit, the deviation is very small, and the same for temperatures. The same it's possible to say when we decrease accretion luminosity. In this case, the deviations decrease too, spectra from the spectra of undisturbed model atmospheres. And a very interesting thing connected with solar abundance atmospheres, because in undisturbed model atmospheres we see some absorption edge for hydrogen-like iron. And why is this edge rise? Because opacity here is much larger than here. Therefore, spectrum here rise in upper layers with small temperatures, and therefore we see some depression in the flux. So here flux rise in this part of the atmosphere, and before edge here in more hotter layers of the atmosphere. That's the reason why we see some edge. In heated atmospheres, you cannot see any edge. It's disappeared because all of part of the spectrum, this part and this part, arise in the same geometrical and physical part of the atmosphere here with the same temperature, and the edge disappeared. Using this approach and some parameters, we computed these curves only for one log G, of course, unfortunately. For helium, pure helium model atmospheres, and you see that heated model atmospheres give a little bit larger color correction, a little bit smaller dilution factors, and less prominent changing at high luminosities. But the most interesting thing connected with solar composition atmospheres, because in models with solar chemical composition, we predicted some deep depression at relatively low luminosities, about 0.1 Eddington luminosity, due to existing of this edge. You see that in heated atmospheres you don't see any depression here in this luminosities, and therefore our models predict that any features connected with absorption edges have to be disappeared if additional heating in atmospheres, if accretion takes place in during the end phases of the burst. And it's possible to compare our results with observations. The first of one for helium accreted atmospheres. It's in ultra-compact object with this title. We believe that it's almost completely helium accreting system. And you see that with the same fitting parameters, our heated curve gives very good description for low luminosity part of this observed curve, normalization versus volumetric flux. And this part of the observed curves described by undisturbed theoretical curve. And there is some transition part of the luminosities when something happens, transition between unaccreted situation to accreting systems. And almost the last slide, it's not our result, but our colleagues from Canada. Andrew Kamek is the leading scientist of this investigation. They showed that observed curves, here it's k to minus 1/4 to describe not dilution factor but color correction factor. And it's some theoretical curves here, it's this logarithmic scale. There are some hard evidence, so strong evidence that this clocked buster accrete solar composition, matter with solar composition, and for metals too, and we expect this kind of curves. Instead of that, we see this fast increasing of the color correction without any depression, and it was some problem which, to be honest, was clear why it's reason, and now we can at least qualitatively describe this kind of observed curves, and therefore we believe that all of the observed curve normalization, blackbody normalization versus blackbody flux, bolometric flux, could be explained by accretion of material on the neutron star atmospheres in the late phases of X-ray bursts. And this is my conclusions. Thank you. They are mine.
Thank you, Valery. And questions, Alexander?
Is it possible to say something about possibility to non-spherical spherical symmetrical burst? For instance, when you have some special direction of burst and something like this from observational point of view.
You mean some anisotropy factor, or what? Here we computed only plane parallel atmospheres with local spectra, yes. And what kind of deviation of spherical symmetry you mean? Some due to rotation or due to some spots on the surface? What kind of asymmetry you mean?
Yes, it may cover a large part of surface of a neutron star, not spot, but nevertheless it may be.
You mean that only part of the neutron star could be accreted, could be heated due to accretion? Yes, of course, it's possible. It will be some additional parameter when we will compare with observations. Unfortunately, too many parameters.
Questions? And can I ask you about, there you have the spectrum. Maybe can you return back a couple of slides? This one, yeah.
This?
Yeah, one of those, yeah. It does
or
work.
this?
No,
or
later.
This?
Later. Stop. Next one, I think. Next one.
This one?
Next one. Yes, here.
I
think the red curve is very interesting. You have additional flux at low energies, and some additional flux at high energies, right?
So brighter.
So, yeah, it becomes much broader. So this atmosphere, heated atmosphere, it's very thin, like optical depth, I don't know, 5 or something, even less.
For electron scattering.
For electron scattering, yeah. So it doesn't produce Bremsschanken?
Yes, of course.
This is the low energy.
This heated part of the atmosphere is optically thick for low energy photons, and of course he give some additional emission.
So this is Bremsschanken, what you see on the left, on the low.
Bremsstrahlung from this upper.
And this tail, high energy tail, you think it's just Compton scattering from the same?
Due to Compton scattering.
Okay. Okay, good. At least I understand.
Especially, it's especially important for these models with low intrinsic luminosity. Here is accretion luminosity 50 times larger than intrinsic, and all of the photon arise here in the heated part of the atmosphere and Comptonize it then and give this spectrum.
Okay, great. Okay, if there are no questions, let's thank Valery and And we have a coffee break, I believe, for about 25 or 30 minutes. Yeah.
Or Okay, so we're going to start with our next set of talks. And our first speaker is going to be Sergei Tsygankov, who's going to be talking about low-level accretion.
Yeah, thank you. I have quite general talk, title of my talk, because I'm going to discuss few interesting observational effects appearing in the case of very low accretion onto highly magnetized neutron stars. And it means that we are studying X-ray pulsars. So I guess there is no need to detailed introduction. I just want to remind you that these objects have neutron stars with very strong magnetic field, about 10 to 12, 10 to 13 Gauss. They are parts of binary systems. They accrete matter from optical companion, usually via the accretion disk. And due to so strong magnetic field, this accretion disk is disrupted at some radius, which is called magnetospheric radius. So Alessandro already mentioned this radius. This is radius where magnetic pressure equals to the Raman pressure of infalling radius, of infalling matter. And usually people use alpha radius, which is calculated for spherical free fall accretion from infinity. And if we are talking about accretion disk, then usually people introduce some parameter, psi, which should be about 0.5. And to be able to follow my talk, we have to introduce another characteristic radius of the accretion onto highly magnetized neutron stars. It's called co-rotation radius. This is radius where stellar rotation of the neutron star equals to the Keplerian frequency. Okay, immediately from these two definitions, we can introduce some prediction of so-called propeller effect, which claims that accretion is possible only if the magnetospheric radius is smaller than co-rotation radius, because otherwise accretion will be stopped by the centrifugal barrier. It is very easy to understand what happens here using analogy of fastly rotating carousel. So just imagine that you want to jump into fastly rotating carousel. Obviously, you are able to do it only if your velocity is roughly the same as velocity of the carousel. If your velocity is high, it's not a problem. You can just decelerate and then jump in. So exactly the same happens in the case of rotating neutron star. So matter rotates in the disk with the Keplerian velocity, so we have to compare field lines velocity with the Keplerian one. So it means that, as I said already, accretion is possible only if magnetospheric radius is smaller than the co-rotation radius. Okay, then we can consider what would happen from observational point of view in the case of some specific source. Let's consider transient pulsar with variable mass accretion rate. Let's start from high mass accretion rate and go towards lower mass accretion rate. So when we have high mass accretion rate, we have small magnetospheric radius, we have direct accretion, and luminosity can be calculated with this equation where R is a radius of the neutron star. Since magnetospheric radius depends on the mass accretion rate, when we decrease mass accretion rate, the magnetospheric radius is increasing, and at some point it equals to the co-rotation radius. Accretion is stopped, and at the same mass accretion rate, we expect very sharp drop of the luminosity, because now we have to put here, instead of radius of the neutron star, radius of co-rotation, which is much, much larger. Okay, so we can combine these three trivial equations to get very useful equation for this limiting luminosity of transition to the propeller effect. So this is it. Okay, this is limiting luminosity, which is, as you can see, function of fundamental parameters of the neutron star. It's magnetic field, strength, and pulse period. Okay, as you can see, the theoretical part of introduction is very trivial. What do we know about this effect from observational point of view? Actually, not much, because it requires observations in very low flux state. So we need very flexible and sensitive X-ray telescopes. But still, the first evidence of transition to the propeller effect was found already 30 years ago, when during the fading phase of the outbursts from this well-known pulsar of E032 plus 53, the pulsar just disappeared sharply below some critical luminosity. Some evidence of the propeller regime, of the propeller effect, was found in this GIRO J7044 using strong variations of pulse fraction and flux, and in this famous millisecond pulsar SAX J808, where some multiple transitions between accretion regime and propeller regime were observed in the tail of the outburst. Actually, that's it. So what we decided to do is to use modern telescopes in order to obtain as many examples of such transitions as possible. So what do we need? We need to catch outbursts from transient X-ray pulsars covering a wide range of mass accretion rates. It is very desirable to have independently measured values of magnetic field to be able to calibrate this method. And of course, we need sensitive and flexible X-ray telescope. And for this project, we use Swift XRT telescope. So we started this project a couple of years ago, and we were quite lucky. During the last few years, we detected several outbursts from these three classical X-ray pulsars. Here you can see their light curves. And what is great about these sources is that we know everything about them. We know pulse periods, we know magnetic fields from measurements from the cyclotron lines, and we know distances. So we can convert the fluxes into mass accretion rates. And this is the results for these three sources. So as we expected, in all of them, in the tail of the outburst, after some gradual decrease of the luminosity, we observed huge, sharp drops of their fluxes by a factor of 100 during only one or maybe slightly more than 1 day. This is exactly what we expected in the case of transition to the propeller effect, to the propeller regime. And another piece of evidence of the stopped accretion comes not only from temporal behavior, but also from spectral analysis. So these red spectra for these two sources are shown just before this transition. So you can see that they are quite hard, can be approximated with the power law, which is typical for accreting X-ray pulsars. And immediately after this transition, the spectrum changed completely. It is soft black body with temperature of about 0.5 keV. And this is exactly what we can expect if accretion is stopped and we see just cooling neutron star. Okay, unfortunately in SMCX2 we didn't detect this low-level emission because it's quite far away. Okay, now what we can do, we can try to summarize all these examples of transition into one diagram. What is shown here? Here on x-axis is shown the strength of magnetic field determined with completely independent method. In majority cases, it's just cyclotron lines. And here we have combination of limiting luminosity for transition to the propeller regime and pulse period in this strange power. As you can see from this equation, this combination, luminosity and this pulse period, is proportional to the magnetic field strength. So these lines show the prediction from this equation. So in some sense, this is also magnetic field strength. And you can see that measurements obtained from this method, from observations of propeller effect, and independent methods coincide very well. So it means that we can use this method to determine magnetic field in neutron stars even if we do not see any spectral features, for example, in the spectra. Okay, then we apply this method to recently discovered first pulsating ULX in M82. The source is called M82X2. So what we found that in the Chandra data, the source can be either very bright, it's shown here, or it almost gone. If you analyze the light curve of this source, you will find that you can find it in bright state or in the faint state. And the distribution of fluxes is clearly bimodal. So obviously we interpreted this behavior as transitions between accretion regime and propeller regime. We use again this very simple equation, and we got estimate for the field strengths in this system about 10 to 14 Gauss, which is actually coincide with independently measured value from the accretion column model proposed by Alexander Mushtakov. Okay, now I will switch to another topic. So this is another source. Of course, we detected outbursts not only from 3 classical pulsars. This is another one, 0J1008. So again, we know everything about this source: pulse period, magnetic field, distance. And of course, we expected to use this source again just to calibrate this propeller effect model. And we expected to detect transition to the propeller regime. And since we know everything, we can easily predict where we expected to see this transition, slightly below 10 to 34 ergs per second. But surprisingly, during the fading phase of the outburst, the source switched to some quasi-stable accretion and stacked about 10 to 35 ergs per second. Why it is surprising? To understand it, we have to refer to physics of accretion disks, or better to say to disk instability model, which claims that stable accretion at high mass accretion rates requires that the disk should be in hot state. It should be completely ionized, and the temperature everywhere in the disk should be above 6.5 thousand Kelvin. If for some reason at outer radius of accretion disk temperature falls below this critical value, then it causes change of the viscosity, accretion rate drops, and it happens at smaller and smaller radii, and so-called cooling waves start to propagate from the outer radius of accretion disk towards compact object, and we should observe very fast decay of the mass accretion rate, of the luminosity, until source will transit to the propeller regime. Okay, but actually this is not the only regime of stable accretion. Mass accretion rate should be so high to have accretion disk in the hot state, or mass accretion rate should be so low to have the whole disk in the cold state. And here we have some equations from Lasota. And now this R is actually inner radius of the accretion disk. But since we are talking about X-ray pulsars, we know what is the inner radius of the accretion disk. It's magnetospheric radius. So now we can substitute magnetospheric radius to this equation and get expression for this critical luminosity when the whole disk becomes cold, completely recombined, and as you can see, it depends only on the magnetic field strength. Now we can come back to this source, 0J1008. We know magnetic field, it's about 10 to 13 Gauss. And if we will put it here, we will get this critical luminosity about 10 to 35 ergs per second. Now we can check again the light curve, and you can see that it should happen somewhere here. So we consider this behavior of the source as first evidence of stable accretion from completely cold recombined accretion disk in the case of X-ray pulsars. Okay, now we can try to answer the question, can we predict in advance which source will end up its outburst in which state? Actually, it's quite easy to do. We should just to equal this limiting luminosity for the propeller regime onset and this critical luminosity for the cold disk. And so both equations depend only on pulse period and magnetic field, and it means that we can introduce some critical pulse period which divides all X-ray pulsars into two groups. And it depends only on the magnetic field strength. So it is shown here. So this equation is shown with the line. So if pulse period is below this critical value, then it rotates fast enough to produce centrifugal barrier before the disk is able to switch to the cold disk, to the cold state. And we will observe this source in the propeller regime, finally. And actually, for the majority of these sources, we already observed them in the propeller regime. And above this period, neutron star rotates too slowly to switch to the propeller. And this critical luminosity for the cold disk will happen before. Okay, so I came to my conclusions. So first of all, we organized observational campaign for observations of X-ray pulsars with the Swift X-ray telescope, and during a couple of last years we were quite lucky. We detected a few transitions. We were able to use this data to calibrate this method to determine independently magnetic fields in these sources, and we applied it to first pulsating ULX M82X2 and obtained value of about 10 to 14 Gauss in this system. And also we discovered first evidence for accretion from cold recombined disk in X-ray pulsars, and we proposed some method how to determine before the observations if we will be able to observe transition to the propeller effect in some particular source. Thank you.
All right, are there any questions? Okay. Yeah.
So you didn't mention the evolution of the spin period during these different phases. Is there a clear change between spin up and spin down, between the accretion and propeller phases?
Unfortunately, so as I said, we need very sensitive telescopes. So unfortunately, we do not see pulsations. We cannot just, because there are too low count rate in this state, especially in propeller regime.
So you did say, though, that all of these systems, or the ones you talked about at the beginning, had known spin periods. So
Yes.
Are they determined in the accretion phase? Or?
Yes, sure, when they're bright.
So there are these accreting black holes in some low mass X-ray binaries that show also very large variations in flux towards the end of the outbursts. And as you go to the low luminosities, they show a softening of the energy spectrum. And I was wondering whether you have tried to compare this phenomenology with what you see in systems like 4U or 115 and so on, so that, in other words, how sure are we that what we are observing is something related to the compact object rather than some accretion flow phenomenology?
In case of X-ray pulsars, we have two large inner radii of accretion disk. So actually, I don't think we expect at all emission from the accretion disk and accretion flow. So in case of black holes, we do expect, and here we don't. So I think the physics is different there.
You used the luminosity in the propeller regime, where you put the magnetosphere radius instead of neutron star radius to estimate the luminosity. It's fine, but my question is, what is the emission mechanism which provides this luminosity? I mean physical emission mechanism, and say which spectrum would you expect in the propeller regime?
Okay, yeah. As I said, the radius, magnetospheric radius, is very large in accretion disk. And we do not expect any X-rays from, so first of all, what mechanism? So it's so-called magnetospheric accretion. So we still have accretion, so matter still comes to the magnetosphere, it releases its energy, and it's called magnetospheric accretion model. But since the temperature is too low, so we do not expect any emission in X-rays.
Okay, but you do expect some emission. At which energies?
Temperature should be about 10 electron volts. So ultraviolet or...
Okay, so it is ultraviolet, but so what is the mechanism? Is it just what, emission from warm plasma?
Maybe, yeah.
And is it observable at all?
No, because it's high mass X-ray binaries, and optical companions are very, very bright. So we do not expect to see some changes of emission due to this magnetospheric accretion. So what we can analyze only X-ray emission.
I see. Somewhat related question: do we expect what happens with this matter which is thrown out by the propeller? Do we expect some outflows from the system, or it remains bound somehow in this binary, or what?
Yeah, also it model dependent. Yeah, there are a lot of different models, and also it depends on how different is the magnetospheric radius and co-rotation radius. So there are some models of so-called dead disks, when we have just collecting some matter in the dead disk, which is not accreting. Or, yeah, we can expect some outflows. Yeah, sure.
But they are apparently unobservable, based on what you...
Yeah.
Okay, thank you.
Do you see pulsation in the cold disk, in the cold disk state? Do you see pulsations in X-rays?
Actually, no. Again, because of statistics. So we can put only upper limits. So below, I don't remember, 20%.
Are there any more questions? Okay, let's thank Sergey, and if the next speaker gets set up. Okay, so our next speaker is going to be Mikhail Gonastayev, who's going to tell us about accretion columns.
So, good day, dear colleagues. My topic today is about spectra of accretion columns in X-ray pulsars. And in the beginning, I will say a few words about possible regimes of accretion on magnetized neutron stars, and then we will discuss each of them using the particular examples of X-ray sources. I noted once that we don't consider cases of extremely low and extremely high accretion rates, and we decided to limit our service by discussing the formation of continuum only, since the questions about behavior of cyclotron lines also deserve a separate talk. So let's consider pulses accretion rates of which are near the characteristic value of 10 to the 17 grams per second. Until the pressure of radiation does not affect the dynamics of the matter, energy of radiation generated in the bottom of accretion column does not change significantly due to transfer through the medium. And the spectrum formed by the unsaturated comptonization. When the pressure of radiation is sufficient, photons play a major role in breaking accretion matter, and then radiation-dominated shock takes place. So, discussing of sources in the subcritical region, we will based on the observations of source CFX4. In this plot, one can see a new star observations for two different values of X-ray luminosity. It turns out that the hardness of spectrum changes with luminosity. And in order to describe of these changes, we use the model of collisionless shock. It is well known that its height is determined by accretion rate and also by the area of the column. Since the area is proportional to the accretion rate to the 2/7, one can easily obtain the following scaling law for the height of a collisionless shock. It is to obtain just from continuity equation. Since the medium is two-dimensional, it is necessary to determine what plays a role of optical depth in typical determination of comptonization parameter. Let's determine the effective characteristical light of the problem just through the volume of accretion column, then the corresponding effective comptonization parameter will be related with X-ray luminosity. We also use here the continuity equation. For the qualitative description of comptonization, we use a well-known solution for unsaturated comptonization, which was obtained first by Sunev and Tizarchuk. with taking into account the magnetic field on the corresponding coefficient. Define the hardness ratio as well as the considered in the considered observations. We will finally obtain a formula for the fitting. And results of fitting one can see here. Obviously that our simple qualitative model describes observations enough well, but however the hardness is not sufficient characteristic for complete description of the shape of the spectrum, and for the solution of problem and obtained spectrum we have involved numerical calculations. So these calculations are based on the solution of radiation transfer equation in the super strong magnetic field. In the absence of energy conversion in the radiation dominated shock waves, this can be done, for example, by the Fourier method. The transfer equation, which was solved, is shown. We work within a column, cylindrical accretion column, in cylindrical coordinates. The redistribution matrix matrix elements are calculated in second order with taking into account second order Doppler effect and recoil and scattering cross sections were being calculated in non-relativistic approximation, which first be done by Nagel and Mesarch. So the vacuum and plasma effects require special settlement. So our numerical results are shown here. One can see observational curves, and dotted lines is the Fourier results. But however, one should not pay much attention to the cyclotron lines, because it seems very good here, but these results include some numerical problems, and one should pay attention only on the continuum results. Let us now consider another situation when radiation has a significant effect on the dynamics on unfallen plasma. Apparently, this situation corresponds to sources demonstrating very hard spectrum in high frequencies, like shown here. It is clear that solution of the problem about thermal quantization is already insufficient. It is not enough here. So the basic equation of non-stationary radiative transport was in radiation-dominated medium was first derived by Blanford and Payne in 1981. Also, they obtained a solution for particular cases of poor bulk and poor thermal quantizations in plane parallel mediums without magnetic field. In the following papers, As you can see here, the equations were solved for one-dimensional mediums with taking account only gray cross sections, and with using of predominated distributions of velocity in the column. Our task is to make the next step on this direction and to solve the momentum equation simultaneously with the stationary kinetic equation, with both ordinary and extraordinary polarization modes on this equation, and also is taking account the real temperature of media. This formula was obtained first by Zildovich and Levich in 1971. So our preliminary results and present time is based on our previous solution of gray problem, radiation hydrodynamical problem for radiation dominated accretion columns. We use our distributions of velocity for solution of equations of radiation transport. But already we solve the system of these two equations. So temperature is determined interactively simultaneously with solving of equation of radiative transport, while without taking into account the bulk comptonization, second order bulk comptonization. Boundary conditions are typically for scattering atmospheres. So it was a distribution of integrated radiation density through the column, and finally spectra of radiation of an accretion column in gray approximation. One can see a certain similarity between observations and our numerical simulations. So, in our conclusions, in any case, if we had any cheerful man near the column, we would have know much more, but at present time our conclusions based on our simulations, numerical simulations only, and we can say that X-ray continuum is formed in a plasma behind collisionless shock by unsaturated comptonization until the accretion rate is not enough for produce radiation pressure, which will be enough for the creation of radiating dominated medium. And on the height accretion rates, X-ray continuum is formed by bulk and thermal comptonization in the break-in accretion flow in the radiation dominated shock. Not that model have only two parameters. It's accretion rate and here m dot and magnetic field. So I think it's all. If any questions, thank you very much for your attention.
All right, are there any questions? George?
In your equations, at least at the high accretion rate, I see no polarization. Does it mean that you didn't take the polarization into account at all?
No. Taking the polarization into account, it is our future work. It is.
But it is critically important when you have a strong magnetic field.
Yes. I agree completely.
But you do not take it into account.
On present time, not yet.
Okay.
But we want to do here.
Okay, thanks.
In the opposite regime, in the subcritical regime, do you take into account for non-conservative scattering?
We take into account the following process: Doppler effect of 1 and 2nd order and recoil. It's all. Redistribution function.
Are there any more questions? Okay, in that case, let's thank Mikhail again and our next speaker. Okay, our next speaker is Konstantin Posnov, who will tell us about propelling the neutron star.
Okay, can you hear me? It's okay? Okay, thank you. Fine. Okay, I'll discuss some our recent work about quite different, very well-known star, Gamma Cassiopeia, which everybody can watch from your garden or balcony each night. And this is a well-known B star, and the closest and the brightest B star on the sky. And I'll try to show you that some features of so enigmatic X-ray emission from this system can be explained in the model where the neutron star rotates inside the quasi-spherical shell of plasma, of hot plasma, and this plasma shines in X-rays and produces all the features we observed in this particular system. So this is a plan of my talk. I'll remind you in a few words about quasi-spherical shells, how they do form around the accreting neutron star, and the propeller. And then I consider the propeller regime in quasi-spherical shell and some differences from disk accretion, which we discussed so far. And then our recent XMM new star simultaneous observations of this system, and also sketch the evolution of the scheme for this kind of sources. So let me remind you that this is a Gamma Cas, and this is a Cassiopeia constellation, and it is a 16 solar masses B star of the spectral type. It enters into a binary system with 200-day period of very low eccentricity, and the secondary companion, which is still under debate what kind of nature of this companion is, is the order of one solar mass, and in fact, this gamma Cas is a prototypical of X-ray binary B stars with a very, very small X-ray luminosity of order of solar, smaller than the solar luminosity, 10 to 32 or 10 to 33 arcs per second. And the important feature of this X-ray emission from gamma Cas stars is that all of them demonstrate very hard optically thin thermal spectrum with multi-temperature thermal spectrum with temperatures up to 20 keV and high density, and rather bright, rather broad X-ray lines, signaling the velocities up to 1,000 kilometers per second. But in all of them, no pulsations have been detected so far. There have been, since the discovery of X-ray emission in the early 80s, there has been a lot of papers devoted to the nature of the objects. Either this is a neutron star or a white dwarf, maybe, and another kind of objects or models, appeared which propose that the X-ray emission is produced by some features in B disks, rapidly rotating disks around B stars, not related to the secondary companion. So the model is based onto the quasi-spherical accretion, and I remind you that there are basically two types of quasi-spherical accretion onto the Comtoc objects. The standard Bondi-Hole Littleton accretion, when the matter, the Bose shock is formed and at the gravitational capture radius, and the matter freely falls toward the magnetosphere and enters into the magnetosphere and comes to the poles of the neutron star, magnetized neutron star, and this regime is okay when the plasma cools down and the characteristic times of plasma cooling is smaller than the free fall time from here to here. And but the important and this is realized. Our analysis showed that this is realized for rather high X-ray luminosity, because the main coolant of the plasma in this picture is the Compton cooling by photons which are produced near the neutron star surface. The plasma is very hot, and but if it cools down, it has time to cool down, then this regime is realized. But another regime, we realized it quite recently, that and there are some papers related to this regime, when the cooling time is larger than the free fall time, which is realized that luminosity is smaller than a few times 10 to the 36 in this quasi-spherical case, then not all the plasma can enter the can pass through the magnetospheric boundary, only those which has, so I would say that the plasma entry rate through the magnetosphere is regulated by cooling, plasma cooling near the magnetospheric shell, magnetospheric boundary, and the accretion is onto the poles of the neutron star is smaller than the Bondi value, and there are some matter which is collected, it accumulates above the magnetospheric boundary, and it should be convective. It can be shown that the temperature gradient here is more than super adiabatic, so the convection and turbulence is being developed in this shell. And it is interesting to see, are there any signatures, observational signatures of these hot shells around such neutron stars. But when we do have some accretion even on the poles of the neutron star, then it's almost impossible to notice this small addition to the X-rays which are produced near the poles in the accretion columns in the neutron star. But our idea was to see what happens if the accretion is switched off, for instance, by the rapid neutron star rotation, a sort of propeller regime, then just this plasma shell would be present in this system, and we try to search for observation signatures of such hot shells. So it is quite a few equations. It's quite simple to calculate the structure of the shell and estimate the densities, the temperature, and emission measure of this plasma, and normalize to the observed X-ray luminosity and mass of the compact object. And the temperature basically is virial or photovirial value, and it depends on the magnetospheric radius, but it is of order of 20 keV. And emission measure, it's important, is of order 10 to the 55, can be 10 to the 54, 10 to 55. And mu is the standard magnetic dipole magnetic field strength of the neutron star. So let's look in just a few simple equations. If you write down phi component of the momentum equation in such a shell, you see that it depends on the stress energies, stress component of the stress tensors, and the stress tensor can be calculated quite easily in this spherical case because the phi component of the velocity can be we can separate variables, and in this case this guy dies out, so we left with only this term, and this term can be written down as through the through the viscosity prescription and the stress in the shell. We can integrate this equation to obtain this one, and here is m dot through this shell. But in the case of no accretion, the left-hand side of this equation vanishes, and the equation becomes even more simple, and the constant of integration just says how much angular momentum is being passed through such a system without accretion. So we can solve this and obtain the distribution of angular momentum in this hot shell, which is not accreting but still hot and convective, and this allows us to obtain the spin-down law. A spin-down law which is different, of course, from the standard propeller case in the disk case, for accretion disk, for example. And what is important here is that the spin-down time in this case is rather high. It depends on the period of the neutron star, and it also depends on the velocity of the captured matter in this in the bonding Hoyle case. And if we relate it to the orbital period in a binary system, and you will find that this interesting formula which shows it's very strongly dependent on the velocity of the captured matter. And in the time could be very long compared to the standard propeller case. So we expect, the summary of the expected hot shells, they must have this 10 to the 55, the plasma should be hot at multi-temperature, and the typical luminosity must be of order of solar luminosity or smaller. No X-ray pulsation should be present, and because of this turbulent character of motions, the plasma velocities could be of order of 100,000 kilometers per second perfectly. So if you have some cold matter close to the shells, then iron K line features should be observed, and lifetime of this could be of this propeller regime in this hot shell could be as long as 1 million years easily, and such system should be observable among faint X-ray binaries in the galaxy. So let's look what we see from gamma CAS in more detail. we made observations XMM Newton and new star simultaneous observations for about 30 kiloseconds. Very Fermi 25, Fermi 26 lines are easily seen there, and also Fermi KL line, and this spectrum from up to 60 keV here, shown here, XMM and new star simultaneous observations, can be perfectly fit with Bremsstrahlung component with a temperature for the 16 keV and two component, it's a PEC component, KT 8.5 and 1 keV, with a total emission of 10 to the 33 x per second and emission measure of a few times 10 to the 55. So this is exactly what is expected from such hot shells. And another interesting property is that the observed X-ray time variability from gamma CAS is shown here from for RXT observations in different moments. So this is just no evidence for any periodicity, but rather this is a of order of 1 f minus 1 spectrum here, but in the hot shell we do expect the range of in hot convective turbulent shells we expect a range of time variabilities from the minimum time, which is of order of few seconds, which is dictated by the inner radius of the shell, and maximum time scale, which it is the longest time, it is the turnover time of the convective shells from Bondi radius to the magnetospheric radius. It could be of order of a few thousand seconds, so it perfectly fits the expectation here. And finally, what could be the evolution of such binary? And in this, just as an example, consider, say, this particular evolutionary case we calculated. This is take 11 solar mass and A solar mass binary system, and just standard evolution of these binaries. After the mass transfer, you have a lot of angular momentum transfer to the secondary component. Secondary component become of order of 16 solar masses, and the first component, primary component, explode as a EC and electron capture supernova from this mass range with low kick. So the binary remains almost aligned on momentum of the B disk, and the B disk is aligned with orbital angular momentum, and the accretion, quasi-spherical accretion, can be realized in this case onto the neutron star. If it's rapidly rotating enough, we have a gamma CAS stage, and when accretion and when the neutron star spins down, finally we will find here the accretion from a quasi-spherical stellar wind. It is a sort of X-per-se stage. This kind of sources are we suggested they are the next stage in this evolutionary scheme. So my conclusion is that in the case of quasi-spherical accretion, hot shells which are formed above the neutron star's magnetosphere can be observed, very good observed, very well observed as a hot plasma shells, especially around non-accreting stars like gamma CAS, and all the features which are predicted for these hot shells perfectly fits with observations, and evolutionary scheme for such binaries with B stars is low kick electron capture supernova, and the rapidly rotating neutron star exhibits quasi-spherical accretion from the B disk, and in the end it will end up as a long period pulsar like X Perseus in the X-ray binaries. So thank you very much for your attention.
All right, are there any questions? Yes.
Can you put a limit on the period, on the spin period,
Yes.
and on the magnetic field of the putative neutron star, your model?
Yes, the spin period is for gamma Kes case. It is something like my estimation showed. It is something less than 10 seconds, something like that in this particular case. And the formulas which I showed you were all normalized to the standard magnetic field, and it could be of order of 10 to the 12. If you times 10 to the 12, it's not necessary to have a huge field, for instance, in this case.
Any other questions? Yes.
Would you expect if the parameters of the binary change differently in propellant case comparatively to the accreting case? And
no, I think that binaries, you mean the binary orbital period or whatever. No, I don't think so. It should be similar.
yeah, but angular momentum was not transferred in propeller case to the neutron star, or
It's not transferred to the neutron star, of course. The angular momentum is not transferred. But this is very long, if you noticed. It is 200 days. It's very long period binaries and on circular orbits, and even the size of B disk is smaller than the orbital separation in this particular case.
Okay, one last quick question. Okay, in that case, let's thank Konstantin, and if the next speaker can get ready. Okay, so our next speaker is Daniel Mata Sanchez, who will speak about new techniques for fundamental parameters.
Good morning. My name is Daniel Mata Sanchez. I am a PhD student from the Canary Island Astrophysics Institute in Spain, working under supervision of Jorge Casares and Teodoro Muñoz. And during my thesis, which I have just submitted 2 weeks ago, I have been working on the determination of fundamental dynamical parameters of low mass X-ray binary through optical and near-infrared spectroscopy. So just a quick reminder about what is a low mass X-ray binary. They are binary system made of two components. The first one is a compact object, which can be either a neutron star or a black hole. And the second is a low mass star, a regular low mass star, which is orbiting so close to the compact object that it's able to fill its Roslow and then produce a transfer of matter onto the former. This transfer of matter is due via an accretion disk, which emits the X-ray radiation that allows its the detection of this kind of systems for the first time. So, attending to their long-term behavior, they can be classified as transient systems, those which spend most part of their lives in a faint quiescent state, but exhibit occasional outbursts where their X-ray luminosity rises up to 7 orders of magnitude. And on the other hand, there are persistent systems, which are always X-ray active, or in other words, they are always in outburst. So in order to determine the dynamical parameters of low mass X-ray binaries, we usually just take the third Kepler law, and we usually express it in this way, because even if what we want to measure at the end are both the compact object mass, M1, and the mass from the donor star, M2, there are some parameters of the binary which are not always accessible to us. And in particular is the orbital inclination, I, which is not easy to measure. And therefore, instead of directly measuring the compact object mass, what we usually obtain is the mass function of the system, F. In order to determine this mass function, we have to measure two key parameters of the binary. First, P, the orbital period, which is relatively easy to measure in almost every low mass X-ray binary. And second, K2. K2 is the donor star radial velocity semi-amplitude. And given that in this equation it's a cubic term, its determination is crucial in order to obtain a good value of the mass function. Through the determination of the mass function, what we finally obtain is a restricted lower limit to the compact object mass, which allows us to discriminate between a neutron star or a black hole as the nature of the compact object. So the classical approach to measure this K2 value is to observe low mass X-ray binaries, those which are transient systems, in the quiescent state. Because in the quiescent state, the luminosity coming from the accretion disk is lower. And therefore, what we obtain, if we take an optical spectrum, like for example in this case, this is the normalized optical spectrum for XTE J1118, where you can see first broad emission lines of hydrogen and helium lines, but also there are some absorption lines which are marked with red squares, which are coming from the companion star. In this case, it's a K5 type star. Measuring the shift of these narrow absorption lines coming from the donor, we can finally obtain the radial velocity curve of the donor star and obtain the semi-amplitude value, which is the K2 parameter we were looking for. So this is the classical approach to measure K2, but it's not always available to us. In this talk, I'm going to tell you about 3 different cases in which we cannot apply the previous method. And these cases are, first, persistent systems. Given that the persistent systems are always in outbursts, the contribution of the accretion disk to the total luminosity, both in the optical and in the near infrared, is that high that completely outshines any trace of the donor star. So we cannot detect the absorption features, and therefore we cannot apply the previous technique. The second case is those low mass X-ray binaries, which are transient systems, but there are some of them that during the quiescence, even in this state, the accretion disk is bright enough to again veil completely any trace of the donor. And finally, the third case are those low mass X-ray binaries that, given that the population of low mass X-ray binary mainly concentrates around the galactic bulge or the galactic plane, they can sometimes be found in relatively crowded fields. And therefore you can have the situation in which you have a field star really close to your source, which hampers any studies in the quiescent state. So the first example for the persistent systems, I will use the low mass X-ray binary harboring a neutron star Scorpio X1, which is the canonical persistent system, which was discovered more than 50 years ago, and is in fact the brightest X-ray source, persistent X-ray source in the sky after the sun. And when you obtain both an optical or, in this case, a near-infrared spectrum of the source, what you find is only the broad emission lines, in this case the bracket gamma line and helium lines, which are coming from the accretion disk. But none of the expected absorption features of the donor are observed. So how do we measure the K2 parameters in this kind of systems? In 2002, Dennis Stix and Jorge Casares realized that apart from the broad emission lines observed in the optical spectra coming from the accretion disk, there were another set of narrow, high excitation emission lines, and in particular the Bowen line, which is represented here. It's a blend of nitrogen-3 and carbon-3 lines. These kind of high excitation lines are produced via fluorescence, and at the beginning they thought that they were being formed in the outermost part of the accretion disk, which are colder. But when they obtained the radial velocity curve from these high excitation narrow emission lines, which is in the top panel, and compare it with the radial velocity curve obtained from a broad helium-2 emission line, which is coming from the accretion disk, they found that they were in antiphase. That means that the Bowen blend lines are not coming from the accretion disk, but from the other component of the system, that is, the companion star. So they are being produced in the inner irradiated phase of the donor star, and therefore we can use them to trace the movement of the donor. Of course, in order to, this kind of radial velocity curves doesn't give you directly the K2 value, because you have to take it, for example, into account that these lines are not being formed in all the companion star, but only in the innermost phase, which is being irradiated. But after applying the necessary corrections, in this case, we recuperated, compiled information from literature of the best measurements of orbital velocities in the system, and with a Monte Carlo analysis, obtained these constraints on the mass of the compact object, which is, of course, an aging star with a mass lower than 1.7 solar masses, and on the donor star, which has a mass between 0.3 and 0.7 solar masses. The second case is, I will use to explain it, a low mass oxide binary named SWIFT 1357, which doesn't harbor a neutron star, but a stellar mass black hole. But the technique I'm going to explain here is valid for both cases, both for neutron star and black holes. So in this system was discovered in 2011 when it went into outburst, and when it was back in quiescent in 2013, we obtained an optical spectrum of the source, and this is what we found. So only broad double peak emission lines of H-alpha, helium-2, which are coming from the accretion disk, are detected, but none of the expected absorption lines coming from the donor were there. That means that in this system, even in quiescence, the accretion disk is bright enough to completely veil outside every trace of the donor. So we cannot apply the classical approach, but we cannot apply either the Bowen technique, because this is a system in quiescence. That means that the accretion disk, even if it is bright enough to veil the donor star, it's several orders of magnitude less luminous than during the outburst. So it's not able to power the fluorescence lines. So to obtain the K2 value in this kind of systems, in 2015, Jorge Casares presented an experimental correlation between the K2 value, which is the parameter we want to measure, and the full width Hall maximum of the H-alpha line in quiescence. This linear correlation is explained when you combine the analytical formula of the third Kepler law, and you assume, for example, Keplerian velocities in the accretion disk, and also you use the Eggleton relation to obtain the Roche law of size in terms of the binary parameters. And when you put all these together, you find that the ratio between K2 and the full width Hall maximum of the H-alpha line, it's a function only of the mass ratio, Q. And that for the particular regime of mass ratios between 0.05 and 0.15, this ratio remains Rowley constant. So you can obtain the experimental linear fit. In this plot, the filled circles are low mass binaries harboring black holes, and the empty circles are those harboring neutron stars. So when applying this technique for the SWIFT 1357, what we obtained was that the compact object mass must be more massive than 9 solar masses. So this must be an stellar mass black hole, and indeed one of the most massive ones found until now in our galaxy. And the third case is a classical, a canonical low mass X-ray binary harboring a neutron star, which is Aquilex 1. It's a canonical transient system because it goes into outbursts every 2 years and then go back to quiescence until the next outburst. But even it has been studied in all the wavelength regime, for example, they even detected millisecond pulsation. This study in quiescence has been hampered so far due to the presence of a nearby field star. So this is the field of view in the first panel, the field of view of the over source, where you can see a few stars. And Chevalier and collaborators performed a point spread function subtraction of these stars, and what they found was that the star A is not a singular star, but a blend of 2 stars, the star A and the star E. And the optical counterpart of Aquilex 1 is star E. So we have a field star 0.4 arc seconds away from our source, and the field star is brighter. So for this reason, the quiescence analysis of this source has not been done until now. To overcome this situation, we performed a spectroscopic campaign on the source using the VLT telescope, which is an 8 meters telescope, equipped with the integral field spectrograph in the near-infrared Symphony. Combining the intrinsic better spatial resolution in the near-infrared and the adaptive optics module equipped in this telescope, we managed for the first time to single out Aquilex 1, so our source, from the field star, this interloper star. And as we are using an integral field spectrograph, we indeed have a spectra for every pixel of this field of view. So we can obtain the non-contaminated spectra of Aquilex 1, which is the blue one. When looking a bit closer to this near-infrared K-band spectra of Aquilex 1, we found first, again, broad emission lines coming from the accretion disk, like gamma, helium-1, but also we detect absorption features. So narrow absorption lines like those of sodium-1 or calcium-1, which are coming from the donor star, which results to be a K4 type star. And as we did not only get one spectrum, but a few ones covering all the orbital phases, we can obtain the radial velocity curve of the donor star, from which we obtain the K2 parameter, which is around 136 kilometers per second. This value doesn't put a strong constraint on the mass of the compact object because the mass function is only 0.2, but it do allow us to put constraints on the orbital inclination of the system, which results to be between 36 and 47 degrees, and also on the distance to the system, which is about 6 kiloparsecs, in agreement with previous determinations from the X-ray bars. So these are my conclusions. In order to measure the fundamental parameters, you usually employ the classical approach of observing in quiescence, but when it's no longer possible, you can use these techniques. In the case of persistent systems, we use the Bowen technique. For quiescent system with a bright accretion disk, we use the K2 to full width and half maximum correlation. And for those systems which are being contaminated by a nearby field star, we can use the near-infrared integral field spectroscopy. Thank you.
All right, are there any questions? Oh, yes, Alexander.
Very nice new techniques. So do you plan to do some more objects? For example, like I'm particularly interested, for example, in this low mass X-ray binary Swift 1753, which is supposed to be a lowest mass black hole.
Mm-hmm. Well, we have an observing campaign on another low mass X-ray binary, which is 17091, which it's in a similar situation to Aquilex 1. It has a nearby contaminated interloper star, but that could be also an option to continue studying this source.
Okay, any other questions? Yes.
When you when you're making this kind of analysis for absorption lines in the optical companion to derive the velocity life curve, do you take into account the fact that these lines are produced mostly on the cold part of the star, which is not illuminated by X-ray emission? Because in this case, these lines should not be exactly prescribed to the center of mass of the optical star, but should be a little bit shifted, and this makes some errors in determination of velocity.
Yeah, for those lines being produced in the inner part, in the Bowen plane, we apply these kind of corrections, but for the lines we are observing in absorption, as they are being observed in quiescence, the disk is not that bright and doesn't affect you that much.
Okay. Any last question? In that case, let's thank Daniel again and all of our speakers. Go eat some lunch.